Hello everyone, welcome back to our channel. This is Dr. Sapna, Assistant Professor, Department of ECE, KIT Kalanya Institute of Technology, Coimbatore. Today we'll have a innovative teaching regarding the project-based innovation. Let us see the project outcome of what is being done in our laboratory. This paper is being published at Frequency. The title of this paper is Performance Analysis of a Flexible Wearable Antenna with Low SAR for Biomedical Applications. Introduction. With the advancement in technology, wireless body area network is a research issue of interest which offers affordable and ongoing patient monitoring services in healthcare industry. In patient monitoring system, multiple body sensors are connected to collect the information and transmit to the healthcare monitoring unit. The device may be worn by the patient or kept close to have the least possible influence on daily activities. So wearable antennas are one of the main part of this body sensing networks. We have designed a wearable antenna which has gained a lot of attention for use in comparable on-body applications. Wearable antenna. Wearable antennas should be flexible and stretchable to adapt to any body movements. Normal conventional substrates of antennas like FR4, Artidoride or Rogers will not be suitable for wearable applications as they are very rigid. The antennas for biomedical applications can be designed by inkjet printing or embroidery on fabrics like jean or polyester. And printed button antennas are available which can be directly stitched onto the clothes. But the difficulty is that fabric antennas are prone to performance degradation due to washing and bending. There are other alternate solutions which can be like nanoparticles, microfluidics and polymers which can be used for wearable antennas. Here in this project we have proposed a PDMS based wearable antenna. PDMS is having the basic characteristics of hydrophobic in nature, that is, it can not absorb any water content. The dielectric permittivity of PDMS is 2.7 with a loss constant of 0.03. This is the design of the proposed antenna. Actually, it is a monopole antenna with a smaller strips and the dimension is 46 by 26. And the back side of the antenna has got a smaller ground plane. The antenna performance has been studied in this and it has got a smaller gain and low SAR, which is basically the specific absorption rate suitable for, which is very important parameter for body applications. So in order to reduce the SAR, we are also gone for a metamaterial. So this antenna is a metamaterial antenna. The structure of the antenna is being shown in this diagram and the unit cell of the metamaterial is a single square slot. These are the parameters of the antenna. The entire antenna has got a dimension of 50 by 50 into 24 mm cube. This is the parametric optimization of the antenna. The dimensions of the antenna like substrate width, length of each of the strips and the width of the strip as well as the thickness is being optimized. The ground level and similarly the period and structure of the metamaterial is also optimized in this study. These are the optimized S11 performance of the antenna for variations of length and strip width. So you can just see that we are getting a very good performance in the rate of S11, which is minus 50 dB approximately, which indicates the antenna is radiating efficiently. So L equal to 7.5 and S equal to 2 mm has got a better performance in this compared to the other values of 7.1 to 7.9 in terms of length, and S equal to 1 to 3 mm. 2 has got a better performance. The feed length and the feed width is also been optimized, and you can just see that feed length of LF equal to 7 mm and the feed width of WF equal to 2.24 has got a highest return loss performance, which improved the antenna. Bending of the antenna, which is basically the important parameter when it comes to biomedical application or the wearable applications, as the body movements definitely will have a variations in the bending of the antenna. Thus, performance should not affect our antenna also. So, here we are also analyzing the bending properties of the antenna along the x and y directions with the different radii. You can just see that along the x axis, the harmonic speed varies from 50 to 100, and similarly in y directions. The performance of the antenna is similar, and it has shown a very close relation even with the variations of the radius in both the directions x and y. But S11 is slightly lower, but it is being acceptable. That is, we are getting up to minus 30 dB. The next is the VSWR performance of the antenna. You can just see that VSWR of the antenna is related with the S11, and it is up to 1.01 is to 1 at 2.45 GHz, which is the design frequency. And similarly, the radiation pattern of the antenna, since it is a monopole antenna, we just see that it is having a figure of 8 pattern at the E plane and omni pattern at the H plane. The gain of the antenna. The gain of the antenna is maximum at 2.4 GHz, which is 1.24 dBA, and at the design frequency 2.45 GHz, it is 1.09 dB, and it is acceptable for a biomedical applications. Lower gain is suitable for bioapplications. Specific absorption rates. Whenever we go for biomedical application or on-body performance, SAR is a very important parameter. SAR is the measure of the rate of RF energy absorption by the body from any surface or the antenna here. Normally, the FCC recommended SAR value is 1.6 watts per kg for 1 gram of tissue or 2 watts per kg for 10 gram of tissues. Now, when we analyze, we can just see that the antenna has been placed on a arm, and it has been placed at different distances from the arm, like a 2 mm, 5 mm, and 10 mm. And for this antenna, 10 mm spacing has got a maximum SAR limitation of 1.69 with the input of 100 milliwatts. And for 2 mm and 5 mm, it has been beyond the acceptable limit, which is 6.35 watts per kg and 4.6 watts per kg. In order to reduce this, we'll going for the metamaterials. So this is the metamaterial integrated antenna as we've seen earlier. So you can just see that a 3 cross 3 unit cell of metamaterial is being placed below the antenna, which improve the soft performance as well as the gain of the antenna. The period of the antenna is 17. Sorry, the period of the metamaterial is 17. That is already given in this parameter. P equal to 16.67 exactly. The enhanced performance of the antenna with metamaterial is being analyzed here. So you can just see the distance between the antenna and the metamaterial is being optimized from different heights at h equal to 24 mm. You can see that it has got a better performance with the gain, SAR reduction as well as return loss. And the radiation patterns of the antenna is also being improved here. The backside radiation has been reduced, which also drastically reduces the SAR performance of the antenna. Since omnidirectional antennas are basically the monopoles, here introduction of this metamaterial made the antenna performance to be improved at the one direction. The red indicates the E-plane radiation pattern of the antenna, and the blue indicates the H-plane radiation pattern of the antenna. You can just see the backlobes are reduced here in this radiation pattern, the metamaterial integration. The specific absorption rate of the monopole antenna on the body with respect to different distances as before, it's been shown here, and it has seen that it has been improved in all the distances up from 2 to 10 mm. You can just see that SAR performance is 0.52 watts per kg for 2 mm, 0.45 watts per kg at 5 mm, and 0.28 at 10 mm. So this is very much advisable for biomedical application because of this reduced SAR. Fabrication and testing of the antenna. The antenna is been fabricated on PDMS substrate as I said earlier, and it has got a thickness of 1 mm dielectric height. Same substrate is used for making the metamaterial also. The antenna has been fabricated by wire mesh technology. The copper plates are sticked on to the substrate, and we are measured using a network analyzer. You can just see the performance of the antenna. It has been S11 performance measured on the network analyzer, and the radiation pattern we have been measured using an anechoic chamber. In the anechoic chamber, which gives us zero zone patterns. The measured results are shown here. The comparative return loss performance during simulation and measured are compared with and without metamaterials. Simulated ones are shown in the red line, and with metamaterial and without metamaterial. You can just see that with metamaterial, the radiation gain as well as the S11 performance of the antenna has been improved. 2.45 gigahertz, the simulated and measured S11 are very closely associated, and the gain is very much improved with the performance of the metamaterial. The measured radiation plots are shown here. Again, with and without metamaterial, you can just see a better performance. Compared to the simulated antenna, during measurement, you can just see there's a decrease in the magnitude levels during measurement. That may be due to the fabrication misalignments, and which can be tolerable, acceptable to the limits. The conclusion, you can just see that the designed antenna was operating at 2.4 gigahertz and it has got a bandwidth of 110 megahertz. And the S11, as I said, it is closely minus 50 dB, and the gain is 1.09, which has been improved using a 3x3 metasurface, which is equal to 3.2 dB. And the antenna is constructed with the PDMS substrate of 1 mm thickness, and the total dimensions of the antenna is 46.8 by 26.35 mm square. But with the metamaterial, it has become 50 by 50 mm square. We have just made it in a metamaterial assembly. The SAR of the antenna, which was around 6.35 watts per kg at 2 mm, was very much reduced to 0.524 watts per kg using the metasurface at a distance of 24 mm below the antenna. And this antenna is very much suitable for a biomedical applications. Thank you.